But anyway, this is an update on the Miocene simulations using ACCESS ESM 1.5. So you've probably heard me talk about my Miocene simulations in the past. Here is like the next iteration of what I'm up to. So building off previous work that I've done with the GFDL model, we have a couple of different paleogeography reconstructions. On the left, we have the MioMIP, which is the Bells 2021 dataset, and on the right, we have the Strauma 2020. So it's an alternative reconstruction of the same time period. And well, you can see immediately there's some just small changes everywhere to ocean gateways, and especially in the Arctic, there's quite some differences there. So in the GFDL model, we found that those changes to those gateways had some interesting implications for where you get deep water formation. To kind of summarize that very briefly, in the North Pacific, in the MioMIP case, we got North Pacific deep water formation and Southern Ocean deep water formation, and not much North Atlantic deep water formation because we had a lot of fresh water come from the Arctic. In the right-hand side case, we got a different preference for overturning, whereby with these gateways coming in to block some of that Arctic flow, we then started going an AMOC under this configuration. So I think my conclusion from that was that the Miocene is particularly close to like a transition between PMOC and AMOC, and that is actually reflected in the proxy records as well. So it's kind of a cool different set of overturning states that we got from the GFDL model. So the question then, what happens? All right, so this is summarizing those results I've just described. I won't linger on these too long because I just presented them, at AMOS and other places. But yeah, North Pacific in the Bells paleogeography, and predominantly North Atlantic deep water formation in the Strauma case, and always Southern Ocean deep water formation in all cases. Now, moving on to the ACCESS ESM simulation. So I've tried to do similar kinds of experiments where we're running 1 times 2 times and 3 times CO2 with just that initial topography, the MioMIP Bells 2021 topography. And what I got initially was that in the 1 times CO2 case, the ocean was kind of nicely ventilated in the Southern Ocean and the North Atlantic, not the North Pacific. We're not getting PMOC in the ACCESS model. But in my 2 times and 3 times CO2 cases, the ventilation was getting killed by stratification from freshwater and or temperature stratification. And so we're getting quite a stagnant deep ocean in the ACCESS model. And I tried to kind of kick off some deep water formation by just adding extra temperature to the deep ocean. So in the 2 times CO2 case, I added 2 degrees to like everywhere in the ocean, and in the 3 times CO2 experiment, I added 4 degrees to everywhere in the deep ocean to try and overcome the kind of temperature stratification which seemed to be forming. And it sort of worked a little bit, and then the deep water just died again. So this model did seem to be quite stubbornly resistant to forming deep water at high CO2. I'm showing here age traces at 2,000 and 4,000 meters depth. I'm sorry, I probably should have explained what an age tracer is, but the blue colors are representing waters that have recently seen the surface, so they're low in age, and the sort of green and yellow colors represent waters that are much older, which means they've been isolated from the surface for much longer. So this is kind of an increment of how long a water parcel has seen, how long has it been since the water parcel has seen the surface. So clearly in our high CO2 cases, the deep ocean is just not getting ventilated. And I found this to be quite an unsatisfactory result because, in lots of other experiments, you do still get deep water formation at high CO2 if you allow the ocean to kind of adjust to the boundary conditions properly. So probably the culprit for this is that the ACCESS ESM is just much higher climate sensitivity than the GFDL model. And even though I thought it was a smart idea to initialize the ACCESS model from our nicely spun up GFDL cases, it turns out that the ACCESS model just gets way, way hotter everywhere. And that means that you do build up like this kind of hot very hot at the tropics, but just kind of hot everywhere, so that the deep water formation regions are then kind of stably stratified by this extreme warmth. So using the left-hand side model simulations to initialize the right-hand side model, in hindsight, that was a bad idea. Don't recommend. Now, sorry, this is getting back to GFDL results. I'm a bit scatterbrained here, but okay, so on the left-hand side, this is the kind of salinities we got in the 1 times 2 times and 3 times ACCESS model, and on the right-hand side, that's a comparison with how the salinity looks in the GFDL model. And you can see that in all cases, the ACCESS model is getting saltier in the Atlantic and fresher in the Pacific. So that kind of the distribution of runoff and precipitation minus evaporation is favoring more kind of the freshening in that North Pacific region. I guess where the precipitation was kind of ending up in the Arctic in the GFDL case, it's now ending up more in the North Pacific. And because of that strong connection between the Arctic and the North Atlantic, that then means the Atlantic gets saltier in all cases. I'm just going to move on from that. We don't think it's particularly salt that's causing the problem. We think it's temperature. And so, yeah, I tried doing a different kind of idealized initialization where I just kind of set a uniform profile of TNS, a uniform profile of temperature with depth, and it just kind of, that also didn't work. So I went kind of the nuclear option of just like hard reset the temperature to be just a single number everywhere in the ocean, because I was just like, let's just find a state where there is just no stratification at all. So like a single number for salinity and a single number for temperature at these higher CO2 levels. And those numbers are based on what the global mean was at the end of like a 1,000-year simulation at each level. So these numbers are informed by what the global temperature was in those previous ACCESS runs, but now I'm just applying a global temperature like absolutely everywhere to like break the stratification. I just don't want there to be any kind of stable separation between the top and the bottom of the ocean. So this does seem to work to actually flush out the deep ocean. Now, this plot is like the meridional overturning that we get after we set up those initial conditions. Now, the top row is actually not, that hasn't been reset. That's just like the end of an 1100-year run at 1 times CO2 in the Miocene. But the bottom 2 rows are showing you like stepwise changes at 2 times and 3 times CO2, moving it. So you look at what happens after 100 years. Southern Ocean's just going bonkers, just like churning out, because it's just like way too hot now in the deep ocean, which is actually kind of what I was trying to do, make it hot enough that it just has to ventilate. So we get something that looks like a pretty reasonable Antarctic bottom water formation, but just kind of really invigorated. But in fact, what happens is as we spin that up, so I've got to 900 years in a 2 times CO2 case and 700 years in a 3 times CO2 case, is that overturning actually kind of decays quite substantially in the Southern Ocean. You still get something, but in like the 3 times CO2 case, it's almost gone. The deep ocean's pretty much gone back to being not ventilated anymore. And in the 2 times CO2 case, I'd say that is still like some degree of ventilation. And this is tracking like a sort of continuous index of northern and southern deep water formation. You can see the northern cells actually holding up reasonably well through the simulation. It's not really dropping off, but I think that's actually picking up this kind of strange Mediterranean feature here, because this index is just like picking up the maximum value of the northern and the southern component. So that red curve is really just tracking the maximum strength of this thing here, which is like the Mediterranean Tethys Ocean, whereas our Antarctic bottom water formation is like massively invigorated and then just dies away. So getting down below 10, I mean, it's still something, but it's less than I might have expected. But the good news is that, like, in terms of trying to achieve ventilation in the deep ocean, I think we have achieved it. So if you look at like now some time slices of age, and this is all the 2 times CO2 simulation, On the left-hand side, we've got age at mid-depth, which is 2,000 meters, and on the right-hand side, it's age at 4,000 meters. And yeah, so you get this like flushing out at the beginning, you get very strong ventilation in the south and the north, and then as time goes by, it sort of eases off, and you get you sort of move back towards a poorly ventilated North Pacific, but still some Southern Ocean deep water formation, some degree of North Atlantic ventilation, but it's kind of it weakens off, and it's not as deep as the Southern. In the 3 times CO2 case, similar story. You get that like flushing out of the north and the south. Over time, that sort of that ventilation weakens, and then you. But the kind of interesting thing is that I think we're actually pretty much losing our deep water formation in like the very bottom, and the Southern Ocean's not really reaching the bottom anymore. So Southern Ocean deep water formation is not like properly ventilating the deep. Whereas I think you look at this one, the 2 times case, it's definitely getting down to 4,000 meters, that ventilation, but here I think it's basically gone stagnant again. So yeah, I think one big conclusion I get out of this is that the ACCESS model really doesn't seem to want to have like top to bottom Southern Ocean deep water formation at high CO2, even if you really try to like give it conditions that might be conducive to that ventilation, it just somehow the temperature profile goes towards a more stratified configuration, and you lose your Antarctic bottom water. So yeah, conclusions I get out of this: be careful with transplanting initial conditions from one paleo model simulation to another. It can cause problems if you don't have a good match of climate sensitivity. Yeah. Sometimes a hard reset of initial conditions is actually the best, even though that does force you to run your model for a long time to re-equilibrate. Yeah, if you go for something that's super idealized, that can be a way of like breaking out of a previous state. But you have to think carefully about how you do that. But we do have some interesting configurations that we've now got. So we've got Miocene simulations at 2 and 3 times CO2, which are either A, super stratified, B, vigorously ventilated but transient, or C, like somewhat re-stratified but still kind of some deep water formation. So I think these are going to be quite good analogs for looking at different states which are relevant for like rapid warming, or a more well-ventilated hot ocean which is equilibrated over time. We can look at things like deoxygenation of the ocean, a collapsed AMOC kind of state, and these simulations are feeding into some student projects where we're looking at the wombat model and what this means for like how oxygen and other biogeochemical traces will respond to these kind of big changes.